You've probably heard the terms AC and DC, and in this video I'll explain what they mean. DC comes from the words direct current, but it's become a thing of its own now, a kind of word of its own, similar to ATM. ATM technically means automatic teller machine, but people frequently say the ATM machine, as if you're saying automatic teller machine. Same thing with DC. DC has come to mean something all on its own, so even though it comes from direct current, we very commonly say DC current. So DC, the main idea to think about it is the word direct. All right, the main source for DC is a battery, so that means that in the labs you did, you were using DC, and you were becoming familiar with the concept of DC, and that's all we've really used so far in this class, is DC current, DC voltage. So here's your familiar battery connected to a light, and we have this idea of charges moving like this, like cars on a road or children running around in circles. And even though we know the charges are really negative, we draw them like they're positives, and the current goes like that. The voltage on the battery is ideally steady at about 6 volts, not changing. And so the current is always the same through this circuit, always in the same direction. It's direct. We call it always in the same direction. So we call that DC. If you were to graph that for our 6-volt battery, the voltage on this battery, if you were to graph it versus time, it would be a really simple, boring graph. It would just look like that. The voltage on the battery just stays constant, always positive, always pushing the current this way. And similarly, if you were to graph the current, it would also be constant. DC, this kind of idea of charges always moving in the same direction with a constant voltage source, is what's required by your cell phone. It's also required by a computer and the calculators, both the TI-89 and the handheld dollar store calculators. It's required by LED lights. All of these things require that constant voltage source to stay steady. By the way, anything with sort of smarts, what we call tech today, that can sort of think, like computers, calculators, phones, that we can program and have apps. These all require DC, and they basically work on a binary system where they treat 5 volts as a 1 or a yes, and 0 volts as a 0 or a no. So they're built, and this is from a standard that was established decades ago, and they're all on that standard. So they're expecting something like a 6 or 5 volt constant voltage source in order to operate. AC comes from the words alternating current. And again, AC has become a thing of its own, an expression that just has a meaning of its own. So even though it comes from alternating current, you normally say AC current, AC voltage. And AC is very different. An AC source pushes charges, just like you would expect them, battery like this, but then it pushes them in the opposite direction. And so the charges move this way, and then they move that way. They move back and forth in the circuit. They kind of wobble back and forth instead of going around and around and around like that. The verb that I've seen used and that I like to use is the word slosh. This is a word you would use for water sloshing back and forth. You put your hand in the bathtub and did this with it. Or you had water in a tube and you kind of went back and forth, getting the water to go back and forth. Slosh is what the air does in your lungs. You breathe out, you breathe in. You breathe out, you breathe in like that. Air going back and forth. Except for you with the air, you're getting new air each time. With the charges, it's the same charges going back and forth like this. So an AC source is like a right side up battery, and then immediately switches to an upside down battery, and then back and forth, pushing the charges this way, then pushing them the other way, clockwise, counterclockwise, back and forth. How fast does it do this? How quickly? 60 times per second. Why this? Why 60 times per second? Is that some natural thing? And the answer is absolutely not. This is a standard that, again, was invented, I believe, over 100 years ago. We could make AC sources go back and forth at other frequencies, and there may be cases where they do, but this is the common standard in the United States. 60 times per second back and forth. That's very, very quickly, faster than I can simulate. 60 times back and forth per second. Your most common source for this type of current and voltage, this alternating current and voltage, is the wall outlet that you're very familiar with in your home. It looks like that. And there are other shapes too, depending on whether you're plugging in something that does not need to be grounded or something that has a higher voltage like an electric dryer or an air conditioner. You'll see other arrangements of the holes and other shapes here, but this is the most common one. One voltage, the other voltage, and ground, like that. Okay, this is a common symbol. I wrote AC source here, but this is a common symbol for an AC source that you would put that in a circuit exactly where you would normally put a battery. And the difference is it's pushing and pulling, pushing like this, clockwise, counterclockwise, clockwise, counterclockwise. If you were to graph this, it would look like this. Right? Like a battery positive, then the other way. And it's not instantaneous. It's not square like that. It's rounded. And if you've learned this in your math classes, you should be familiar with what functional shape this is. This is a sine wave. It has the same shape as a cosine wave, which would start up here instead. But it's a sine or a cosine wave. We call that a sinusoidal shape, like a sine wave, like that. So it's a smooth transition from 0 up to positive 170, down to negative 170 volts, up to positive 170. And I picked 170 because that's the average for a typical wall outlet, the average maximum and minimum. Up and down from positive 170, when it's most pushing things this way, then it gets weaker, 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 and then it starts to push the charges the other way. That's when we say it's negative, like an upside down battery pushing them the other way, till finally it's got a maximum of 170 volts upside down, pushing them this way, and then it gets weaker again back to 0, and it repeats. 170 and negative 170 are the common maxes and maximum and minimum for the United States for our wall outlets. But if you average this out and see what, on average, what kind of voltage am I getting in absolute value, it turns out to be about 120 volts. Depending on where you live, it could be as low as 110. It's between 110 and 120, usually across the United States. There's no fixed rule that has to be exactly 120 or 110, so it depends on where you are. But my house, where I live, I've measured it, and it's about 120 volts. And so that's why you'll often hear people talk about wiring a house at 110 AC or 110 ACV or 120 ACV, or they might even say 115 or 110 to 120. It's just it's in this range, AC voltage. Now, this is complicated, right? Back and forth, charges sloshing back and forth, a more complicated graph. And our calculators, cell phones, and computers don't use this. They don't want this. They want that constant DC voltage. So the question you might be asking yourself is, why? Why would we ever have this kind of voltage? Why would we engineer our electronics to create a wall outlet with this sloshing AC voltage? Well, it is used by some motors. There are some motors that are designed specifically to be used with AC. And it can be used by a heater. A heater will get warm, and think of why a heater is just a resistor, a big piece of metal, and the charges go back and forth in it, just like that, just like we've always done in class. And what happens to your hands when you do this? They get warm. So a heater doesn't care if the charges are going one way and you get that friction and they get warm, or back and forth. It's still going to get warm either way. Your incandescent light bulb is basically a heater that glows. So likewise, it doesn't care whether the charges are going one way, as they do in our lab with the little light bulbs, or back and forth, as they do in the light bulbs I have in this room. That's an incandescent old-fashioned light bulb, not an LED. So why? Why would you make this thing? Of course, it can be used by these things, but both of these can use direct DC anyway. So why? Well, there are two reasons. The most efficient way to generate electricity from something moving, say moving water or boiling water and making steam and making it blast and turn something. If we can make a wheel turn, the most efficient way to make electricity is to use magnets and use a generator. And when you do that, it creates a voltage that looks like this. So this is generally, the AC is generally easier to make traditionally. Not solar, I'm not talking about solar, I'm talking about the making of voltage, creating voltage and electrical energy by causing a wheel to turn. That turning action creates this. To understand that fully, you have to learn about magnetism and then generators. That's a topic in AP Physics C. It also travels better. There's less energy loss, and if you look at the high power lines above Country Day in the back near the fields, they have an extremely high voltage because that travels better, and they are AC. There's less energy loss. There's even a movie about this. It's a story about Edison, Westinghouse, Tesla having debates and arguments around 1900 over which one is better. Edison was for DC, Tesla, Westinghouse were for AC, and of course they won. That's what we have today, AC in our wall outlets. All right, and then finally, learn about AC to DC conversion. Here's the problem you face, especially these days with so much tech. The wall outlet puts out ACV because we're getting that from the power company and it travels better, and it looks like that. But some of the most common devices you use, your phone, your laptop, they need DCV. So does a TV screen, for example. Need DC voltage. They need this. So you cannot plug these directly into the wall because these need this. And in fact, this is 170 volts. These actually need, say, 6 volts for the intelligent parts of it and, say, 25 volts for the screen display. So they need a constant voltage that's a different value and not changing. The solution to that is what we call an adapter. And this is an old-fashioned adapter. You probably see these. AC, you plug this into the wall, so AC voltage goes in there. DC voltage comes out here. This is the adapter for my laptop. And this is another adapter. AC goes in here, DC comes out there. Adapter's a little box that does this conversion. The adapter contains 2 things which you will not be tested on. This is the end of the circuits chapter. Diodes, that's the symbol for a diode. If you want to look them up, they're very simple what they do. I may put there's some practice questions on the review packet that are only bonus. So if you want to learn what a diode does, it's pretty simple. It's like a one-way street. That's a possible bonus. And a transformer, which will absolutely not be on the test even as a bonus, because to understand a transformer, you have to understand magnetism, which is part of AP Physics C. So you put together 4 of these and a transformer and something else called a capacitor to smooth things out. You put those in a box and you can convert this to this. And this is a typical adapter box that does that. And it has these elements in it: diodes, transformer, and a smoothing capacitor to make it nice and level.